Okay? So is everyone here? We're good? All right, so what we're going to do then is look first here at line symmetry. Okay, so I'm going to zoom in a little bit so we can see a little bit better. Feel free to follow along in your book. Okay, so a figure has symmetry if a rigid motion exists that maps the figure onto itself. A figure has line symmetry, or sometimes called reflectional symmetry, if a reflection maps the figure onto itself. Each of these lines of reflection is called a line of symmetry. So here, if you look at this, we have this little like crescent moon shape. Okay, right there. And you can see that if we drew a dotted line like right through the middle, okay, which you could call that, like you call it a line of symmetry, but it also could be like a line of reflection, right? If we reflected this top piece of this moon over this line of reflection, it would match up perfectly to the bottom piece of the moon. And that's what makes it a line of symmetry, right? Okay. Are there any other lines of symmetry in this moon shape?
Yes.
Are there any lines of reflection we could draw?
No.
So, right, answer, yeah, we can't really do any more than that. Okay? So, what they have us looking at here is like actually like folding a triangle, but I don't think we need to do it. We can just kind of look through it here. So you see what they would want us to do is to trace this triangle on a piece of patty paper, fold it so see that it does in fact overlap itself, and then to use that kind of come up with the idea that there's a line of symmetry there. Okay? So because there's a fold line here, if we were to fold this triangle, it would fold onto itself. That means there's a line of symmetry, right, that goes right through the triangle just like that. Okay, I didn't do a great job there, but you get the idea. Okay. Are there any other lines of symmetry in this triangle right here?
No.
Okay. Anyone see any more? Derek, you see another one? Where would I have another line of symmetry here? Yeah, there aren't any more actually. This is the only one. So this figure has one line of symmetry. Okay.
Is that how it can be cut in half?
Basically, essentially yes. The idea is that if you want to think about like being cut in half, yes, but it's more than just cut in half. It's the idea that
It's like two equal parts.
that would flip onto each other. Yes, reflect onto each other. Okay. Shh. Guys, the talking needs to stop. Okay. You need to listen. I know this is easy for you, but we got to make sure we understand this stuff. Okay.
Are we on the next page?
So yep. Go ahead and turn the next page then, because that was it for that page, right? And let's look at letter D here. So letter D says, okay, to draw the lines of symmetry, if any, on each figure and tell the total number of lines of symmetry each figure has. Okay. So let's look at this right here. Okay. So we know this shape, right? Hopefully it's familiar to us. Okay, so Dominic, what is this shape right here? It is a rectangle, that's right. Okay, so Dominic, can you tell me, do you see any lines of symmetry that we could draw here? I know it's kind of hard to describe, but... So how would I draw it? Just kind of show me with your finger maybe, and I'll kind of like try and... Okay, yep, a vertical one, right to the center. Like that. All right, Ramel, go ahead. The horizontal is the other one, horizontal.
Wait, never mind.
This way?
Diagonally.
All right, hang on. Listen. Okay, if you guys stop talking, it would really, like, you stop annoying each other, too. It's that simple, okay? So anyway, a vertical line, okay, is like this. Remember, horizontal, think the horizon, right? The horizon, that's where the sky meets the ground, and it's a nice, like, very horizontal. Sometimes you have, like, you know, mountains and stuff like that. It's not so, but flat. But, I mean, at least that's the horizon, the horizontal line, okay? So do we have any other lines of symmetry? A diagonal one? I don't think that rectangle would would reflect onto something. All right. Let's see. Okay. Let's see. Let me show you here. So what we're going to do is I'm going to take this rectangle. I'm going to copy it on my patty paper. Okay.
I have a good example right here.
You have your paper right there. Did you fold it already?
Yes, I did.
There you go. See, exactly right. So there's our rectangle, right? I didn't do a perfect job, but you can, believe it, right? At least so. Now, if I fold it right on its corners there, you can see that. Does that match up? I didn't fold right. That's diagonal. Look at the fold.
No, you have to, okay, so put a point on the left upper corner.
Right here.
Right.
Okay.
Okay, put a point on the one diagonal.
Right here.
Yeah.
Okay. Got it. And you want me to line them up, right?
Yeah.
All right. You got it.
I'll probably wrong it.
Wrong.
Okay. Lining it up. You see they're lined up.
Don't say that that's free. Okay.
Right, but here's again, that's good. I'm glad you guys are trying to think about this stuff, but you see, it doesn't work, does it? Now, let me show you, it looks like it, but let me show you. Now, let me show you the other one. So we have a vertical one, we said, right? So that means you should be able to take this and fold it so you can see I do have those parts line up, and there's my vertical one. Okay, so the vertical one does work. Okay, and the patty paper will be available to you if you want to convince yourself, Ikeba, that it either works or does not work. Okay, if you need to convince yourself.
If you don't actually do it, it looks like it would do it, right?
Sure. Okay, now, what kind of shape that's similar to a rectangle would have diagonal? A square. A square would. A square would have it. Okay. All right.
Where would fold that?
How about the triangle here? Let me call on someone. Let's go to Taylor. What do you say here? Does this triangle have any lines of symmetry? One. Where? Show me your paper, and I'll take a look. Yeah, you're right. Yeah, Taylor's got it here, you guys. So here's the thing. There is a line of symmetry, and it's right there.
How could you be able to tell
So how can you tell without using patty paper? Well, some of us here can just visualize that kind of thing, and if you can't, then absolutely use patty paper. And here's one thing though I will say, Jaden. The trick with this one is that it's not oriented kind of a normal direction. If you turn it a little bit, and you look at it this way, you're like, oh, that makes a lot. You can definitely see it a lot more now. And in fact, this triangle is just like the triangle we talked about on the previous page right here. It's very similar.
You can also remember by triangles only have one line symmetry. Yeah.
I can draw a triangle. Well, we'll look at a triangle here in a little bit that has more than one line of symmetry. So anyway, so this one has just one. That's right. Okay. And then how about this third thing here? Let's go to Zaria. What do you think about this one? Are there any lines?
What do you say?
Are there any lines of symmetry in this shape?
Yes.
Say no. Okay. Yes, thank you. And that's okay, Zaria. Thank you. Let's see. Maddie's in the bathroom. She's coming back. Not in time. Ramel, what do you say here, buddy? Do we have lines of symmetry or no? Is there a line of symmetry here? You don't see one? No? Okay. All right. All right, Derek. Where do you see a line of symmetry here?
Right there in the crease of the head.
So if you look, and again, this one's kind of tricky because of the way it's drawn, but I think we could probably fold this shape right along that line, and it would fold onto itself. Okay. Well, so again, sorry, I signed the wrong one. There you go. Okay. So again, we can convince ourselves that is true by taking a piece of patty paper here and kind of tracing it out. And again, I'll give you there's patty paper up front for when we do this on your own. Okay. You kind of trace it out on our patty paper and then fold it. So there's my trace. You can barely see where is that. Hello, there it is. Okay, barely you can see it. Okay, and if you fold it, just like we said. Okay, you can see that the parts do kind of overlap, and then when I unfold it, you can see there's our symmetry line right there. Okay, so there is one line of symmetry.
How would you fold it for
Through the set, your fold line would go right through there, so that this piece would fold on top of this piece. It's a diagonal kind of fold. Okay. Okay. So we're going to skip this first question here about what do you have to know about any segments and angles in a figure to decide whether the figure has line symmetry. But we're going to do the second one though. There is one shape that I can think of, okay, that has an infinite number of lines of symmetry. It's a circle. A circle. A circle has infinite lines of symmetry, right? Because if you imagine drawing a circle, right, you can go like this, and then there's like this, and then this, and this, and this, and this, and this, and this, and you can just an infinite number of lines of symmetry there. Okay. So, and this is kind of an easy question, I think, too. A figure undergoes a rigid motion, such as a rotation. If the original figure has line symmetry, will its image also have line symmetry? Yeah, absolutely, because it's not going to change size or shape, so it should still have that line symmetry. Okay, so that's line symmetry. Any questions on that? Otherwise, we're going to move on to rotational symmetry here. Okay, so rotational symmetry. A figure has rotational symmetry if a rotation maps the figure onto itself. Okay, the angle of rotational symmetry, which has to be greater than 0, but less than or equal to 180, is the smallest angle of rotation that maps a figure onto itself. So if you see here the star, okay, they already drew like the center of the star, which is not, doesn't look like it's quite centered, but I guess we'll just take the, it should be like here, I think. Anyway, this star has a center of rotation right there, and if we rotate the star, they say that the angle of rotational symmetry is 72 degrees. Okay, now how many times do you think we can rotate the star before it goes back to its original kind of position? Yeah, 5, exactly right. Okay, and that's important. Well, that's right, and but that's important to recognize, because how many degrees is one full rotation? 360. If we can make one full rotation in 5 little turns, right? So Jaden just said 5 turns to go the whole way around. Then how can we figure out what just one turn would be?
Divided by 5.
Take this and divide by 5, and guess what we get? We get that 72 degrees, which is what the rotational symmetry is. Okay? So you have to figure out, you have to be able to count, though, the number of times you can turn. Okay? So let's take a look, for example, here at this this triangle. Okay, so we have another triangle right here. I'm going to take my patty paper, and I'll show you guys how you can do this to figure this out. Okay, so we take our piece of patty paper here, and if we trace out this triangle on the patty paper, okay, and I'll try and do this like nice and dark so it can like show up real good. Okay, and I'll draw my little dot. And what I suggest you do is put a little mark at one of the points, and then put that same mark on your patty paper. The purpose of this is so that when we rotate, we'll know how long until we get back to the original. Okay, so here I'm going to rotate my shape and count how many times it maps onto itself. So I'm going to rotate it, and then okay, so there's 1, right? Back around to 2, and then once more. And it took 3 times to go around.
Or you can just count them.
You can just count 2, and that helps as well. But if you want to really see the rotation. So again, if we take 3 turns to go 360 degrees, how can we figure out just one turn? 360.
Divided by 1.
360 divided by 3, which is 120 degrees. So by how many degrees do we rotate the figure?
120.
120 degrees.
Is there ever going to be like, when you divide it, is it ever going to come out?
Could be a decimal, potentially. But again, if you have your calculator available to you, that'll help. Yes, sorry? Because what did we do here? We took our shape and we rotated it all the way till it went back to its original. But we stopped every time it mapped onto itself. So there was once, twice, and then the third time back around got us around there. So we divide 360 by 3. So does that make sense? Sorry, we took our total rotation there and divided by 3.
What if it's like an uneven shape?
Then it would be 0.
So great question. And I don't know, we don't have any drawn like that right here. But like, for example, this L shape right here, okay? It would rotate only once until it matched back up to itself, right? And so we would say this thing has no rotational symmetry.
So like everything that's like not symmetric.
Rotational.
Symmetric, it's just going to be one.
Exactly. If it's just, and because it's true, right? Every shape goes back onto itself if you rotate it 360 degrees. So that's not special enough to then say it has rotational symmetry. It has to be, something less than that. So like 2 times or 3 times or 4 times it has to map back onto itself. Okay. You have a question?
So for like figures on the next page, like when you like how would you what is angle rotation?
I think that's what that means. Sorry, angle of rotation. Oh, we'll get to that. We'll get to that. Okay. Real quick though, I want to show you though. Okay, you said all triangles only have one line of symmetry. How many lines of symmetry does this triangle have?
3.
It's got 3.
Yeah, but how? Because I only see it one down the middle.
1, 2, 3. You see them?
No, not the last one you just drew, because that point would go.
Let me show you. Shh, guys, relax, please. Excuse me. I hope that when you guys have questions, you're a little more patient than you are being right now. Okay? Because that's kind of rude. All right. So let's listen, please. Just give them a chance. Shh. Do you see it? It's an equilateral triangle. So this side. Shh. Thank you. All right. So again, this side. I don't think you guys understand. When I'm talking, I want you to stop. When I stop talking, you stop talking. When I start talking, you start talking. That's really weird to me. Okay? You need to be paying attention right now. I think there's going to be new seats when we come back on Monday. FYI. Okay? So anyway, this side, okay, folds over to this side. Do you see it now, that line of symmetry? There's 3 of them. Okay? So, all right, moving on. Here's our table. Okay, determine whether each figure has rotational symmetry. If so, identify all the angles of rotation less than 360. Why do they have to be less than 360? Because every shape has rotational symmetry of 360 degrees, right? If you rotate anything 360 degrees, it's right back to where it started. So that's why it's not special. We don't call it rotational symmetry then. Okay, so the square. Again, let me grab my patty paper here, just kind of show you how this works. I can't find my pencil now. Figures. Jeez. All right, I'll just use my compass pencil here. Okay. So, again, just if you want some help, trace out your shape on your patty paper. Ooh, and I think I just broke the lead in this thing. Okay. So there's my square, and the rotation point is going to be right in the center. Okay, like that. And so again, I suggest you mark one corner or something like that, one part of your shape, so as we rotate. So again, we're going to count here, right? So let's see here, 1, right? 2, 3, and then 4. So if it takes 4 times to go around, we'll do 360 divided by 4, which is 90 degrees. So that's your angle of rotation.
Why does it match up?
It should match up.
Okay, so I drew my shape, and I made my little point, and I have my pencil here, and I'll turn it, and then it's like off, like, not even on shape it.
So I would suggest don't worry about keeping your pencil on it. Just rotate it kind of freehand, and then it'll match up better that way. Okay. All right, this triangle here. If we rotate this thing, so again, I'm going to try to take this and rotate this triangle here. Okay, you'll actually see this does not. There's my triangle, right? So if I rotate it, it's like, all right, not quite, not quite, not quite, not quite, not quite. And it goes back to the original. So how many times did I get to rotate that before I went back to the original? I mean, it didn't, it never matched up. Yeah, it was 0, guys. Look, it never really matches back up until I go all the way back around again. And I should have marked it off here, sorry. Okay, but if you see, like, I can't get that to match up really right, and I can't really get this to, like, match up right either. Okay, and so it has to go back to the original. So this has no rotational symmetry. Okay, and then this last one. Anyone want to hypothesize here, Zari? What do you say? 2. Let's see. Very good. I think Zari is right. I'm going to just copy it here. Okay, and again, we'll rotate it. Actually, I should put my little mark here at the top. Okay, just like kind of mark it off. I'll mark it off up there too. Okay. So we rotate, Yep, there's 1, it matches back up, and then back around to 2. So that's me 360 divided by 2, which is 180. Okay. Yes, EK, have a question.
So, like, I don't understand, because, like, if this is
Yep.
on some shapes you'll go 90 degrees, and then you'll go 90 degrees, and then on that one you just went like this, like 180.
Well, because here's the thing, okay, I mean, watch. It's not matching up, it's not matching up, it's not matching up, still not matching up, still not matching up, then it matches up.
Right.
And then I have to go around back to the original, though, so that takes 2 turns.
But that is going back to the original.
Right, and so it takes 2 turns, so...
No, like if you have your shape,
Yes.
right?
Yes.
All right, so turn it a little bit. Keep turning it. Keep turning it.
Right, right.
Okay, so then that's 1. You count that as 1.
Uh-huh, 1 turn.
But that wasn't all the way back. That was just halfway.
Well, what I mean is, it took, like, our paper, like, our... to go back onto itself, that's once, and it takes twice to then make it all the way back around, I guess, is the idea there. Like, it's... I hear what you're... Okay, I kind of think what you're saying.
So then the second one before that,
Okay, this one right here?
yeah,
Okay, so there it's matched back up.
that goes around.
Again, I rotate it,
Right.
never really, you can see, never really, like, kind of matches up right. You see what I'm saying? Until I go all the way back around to the original again. So it's just 1 turn that I can make it in. It takes 1 turn to go all the way back around. Shh. All right, hang on, guys. Shh. We're not done yet, okay? So hang on. I'll collect that in a second here, or we'll worry about that in a second, okay? Shh. Listen up, please. So what figure is mapped onto itself by rotation of any angle?
Oh, the square.
Any angle? Can you give me that count to a square? Again, what figure is mapped onto itself by a rotation of any angle? The square, it needs to be a 90-degree angle, right? If I just do like a, like that, yeah, it's a circle. It's a circle. It's a circle, okay? A circle can be rotated any degree and it will still be mapped onto itself. Okay? So, last thing I want to look at here, all right? We have this shape. Okay, it says to describe the symmetry. So that means we want to describe not only, well, what 2 symmetries do we want to describe here? Rotational and line. Or reflectional, if you want to call it that. Rotational and line or reflectional symmetry. Okay? So let's look at this first. Okay? Well, if we look, they kind of draw in two lines for line symmetry. Are there any more line symmetries you could draw in here?
No.
Yeah, there are. Haley, how would you describe one of those?
It's like, I don't know how to describe it, like in between.
These here?
The 2 points and then the opposite.
Yep, exactly. You have some diagonal ones you could also draw in, so keep your eye out for those, okay, folks? There are sometimes, more than that. So how many lines of symmetry do you have? I see 1, 2, 3, 4. Notice I don't count this one 5 because I already counted that as the first one, right? So it's 1, 2, 3, 4 lines of symmetry there. And then what about the rotational symmetry? Well, if you look at this, okay, we could turn it 1, 2, 3, 4 times there. And so it's 365 by 4, so that gives us the, oops, sorry, can't see it, 90-degree rotational symmetry. Okay? So, wait a minute, before you guys are all done here, because you guys, okay, we're going to do this last one, I want to look at this one, okay? The line symmetry. How many lines of symmetry do we have here for letter B? We're going to have 3, right? Okay, 1 like through there, 1 through there, and 1 through there. So 3 lines of symmetry. And how many times do we turn it before we go the whole way around? 3 as well. So it'd be 360 divided by 3, 120 degrees for the rotational symmetry. Okay? Your homework, your homework is going to be page 106 to 107, okay? I want you to do actually numbers 1 through 16. Yeah, all of them, okay? 106 to 107, numbers 1 through 16 is your homework. Okay.
Right.